So, hi, my dear students. We continue the session here. With the node analysis, we already solved in the previous session some important problems in the mesh analysis. Okay, I think after seeing those two examples, you might have understood how we apply the mesh analysis, particularly when there are current sources, how to apply. I think you got clear idea. Okay, so still it is available on the board. Okay, now the next things that what we are doing here is node analysis. Okay, we'll start node analysis. I know that most of you are aware of the node analysis, but still I start from the beginning. Okay, there are so many important points to be discussed. Okay, so put the heading node analysis, write the point, first point, node analysis, first point, put the heading second method, node analysis. In node analysis, you must remember 2 points always. Fix in your mind. Okay, the first point is that the linear algebraic equations are obtained using KCL plus Ohm's law. Using KCL plus Ohm's law. Whereas mesh analysis, KVL plus Ohm's law. Okay? The linear algebraic equations are obtained using KCL plus Ohm's law. Node analysis is applicable to both planar and non-planar networks. Both planar and non-planar networks. Okay? So these are the two important points. And what is the advantage of node analysis over the mesh analysis? If somebody is asking the question, what is your answer? Mesh analysis, there is a limitation that it cannot be applied to a non-planar network, but node analysis can be applied to both planar as well as non-planar. That is the greatest advantage with the node analysis over the mesh analysis. Okay? So whatever the limitation is there with the mesh analysis, that we can overcome using node analysis. Okay, so we will see now by taking different cases. Case 1, case 2, case 3, just like in your mesh analysis, we'll take different cases because I have designed the cases here in such a way that whatever the problem you come across from any source, whether it's any textbook or any exam or anything it might be, you should be in a position to solve them. That's it. Okay, so that's why I've carefully chosen the different cases here. So first we start with case 1. Note on this network first. Note down this first. Quickly note down first that network, then I will give you some valuable points. Step 1. Step 1. What was the step 1 in mesh analysis? Select minimum number of loops. Here, select minimum number of nodes. Okay? Select minimum number of nodes or choose minimum number of nodes. Okay? There choose minimum number of loops because the number of variables is equal to the number of loops in mesh analysis. The number of variables is equal to or it is related to what based on the number of nodes. Yes or no? Okay. So therefore, you better choose the minimum number of nodes here. Okay. The number of variables, how it is actually coming in node analysis, we will see that. But whereas in mesh analysis, the number of variables is equal to what number of fundamental loops. Yes or no? Okay. Well, now here, choose minimum number of nodes. How do you choose the nodes? First of all, what is a node? The degree 2 minimum node, degree 2 node, degree 3, right? Node. This is also what degree 3, therefore node. This is degree 2. Okay? This is degree 4, 1, 2, 3, 4. This is also node. This is 4 and this is 5. Okay? There are totally 5 nodes. According to the definition, they are nodes, no doubt in that. But in our analysis, what is our objective? We want to choose the minimum number of nodes. For that, what you do is, okay, you select a node with a minimum degree 3. Okay, you select a node with minimum degree 3. So what is the degree here? 3, degree 3, degree 4. Therefore, I can choose degree 2. Let me eliminate it. Let me eliminate it. Degree 2 means the elements are connected in series only always. Wherever you have degree 2, that means there are 2 elements connected in series. Now remember, in node analysis deals with what? KCL. In KCL, algebraic sum of currents. Currents are same when the elements are connected in series. Therefore, there is no need to take any variable between 2 series connected elements. Okay. So finally, how many nodes are there? 3. So what is the logic that you are choosing? Okay. I'm just writing here. Select nodes with minimum degree 3. With minimum degree 3. Understand? Okay. Now, if there are n number of nodes, what is n actually? Minimum number of nodes. N itself is minimum number. After selecting the nodes with minimum degree 3, let us say n is the number of nodes, let us say. That is, n stands for minimum number of nodes. Then out of this n number of nodes, one node is selected as a reference node or datum node, or some people call it zero potential node. Now what are the remaining nodes are available? n minus 1. These n minus 1 nodes are called principal nodes. Principal nodes. Understand all of you? At each principal node, you now indicate a variable v1, v2 and so on. How many are there? Vn minus 1. Therefore, n minus 1 equations required. N minus 1 equations required to analyze the network with n number of nodes. What is n? N itself is the minimum number of nodes after selecting the nodes with minimum degree 3. Is it clear, all of you? Okay. It's a very, very important point to be observed. So you give me any network, I can immediately identify in the first instant itself. Okay. In the first instant itself, I can identify that what are the minimum number of equations required. Okay. To solve that network. How many number of nodes required? That's it. Simple. Out of this, you choose one node as a reference node. Okay. You select any node. Doesn't matter this node or this node, this node. There is no restriction at all. But usually people choose, okay, bottom node as a reference node. Okay, bottom node as a reference node. Therefore, you select this node as a reference node. Then what will happen here? This becomes V1. This becomes V2. Is it clear? V1 and V2. Now, second step. Step 2. Step 2. Step 2. For this, please look at this. I'll give time, don't worry. First look at this. We need to understand the details of this node analysis clearly, okay? Node analysis deals with what? Kirchhoff's current law. KCL requires algebraic sum of branch currents, yes or no? To find branch currents, you require branch voltages. Branch voltages are expressed in terms of node voltages. I think you understand this. Okay? This is very, very important here. Node analysis deals with KCL. For KCL to apply, you require branch currents. To find branch currents, you require branch voltages. Yes or no? Okay? But these branch voltages are expressed in terms of what? Node voltage. So very simple. Okay? So that is why the first step we already done. The second step, what we do is we find branch voltage in terms of node voltage. Therefore, write down here, express branch voltages. Express branch voltages in terms of node voltages. So express, okay, branch voltages in terms of node voltages, and also find okay, branch currents, and also find branch currents. So once you know branch currents, what will you do? Apply KCL. Where do you apply? Apply KCL. Where do you apply? Tell me, where do you apply? At any node you can apply KCL, right? You have a right to apply KCL at every node, and at every node KCL must be satisfied. So to get the equations, we can apply at every node, but to make it very systematic and more disciplined, okay, we apply this KCL at each principal node, okay? Apply KCL at each principal node. At each principal node. Wherever you have a variable, node variable, okay, what are the node variables? Definitely voltages. What are the loop variables in mesh analysis? Currents. Loop variables are loop currents. Node variables are node voltages. Yes or no? Okay. So therefore, apply KCL at each principal node. That means here and here. Don't apply here. You can apply. You can apply here. It doesn't matter. Okay. But more disciplined method, systematic method is that, okay, here you can apply. Apply KCL at each principal node and solve for V1, V2. And of course, and so on Vn minus 1 in general when we talk about, okay. So please note down this first, and then I will execute the step 1, step 2, step 3. Let us execute it, okay. Look at this. What is the second step? Express branch voltage in terms of node voltage, also find branch currents, right? Let us see. Before that, I would like to give you some assumptions. What are the assumptions? The two principal node voltages are assumed to be at higher potentials with respect to the reference node. This is the reference node, okay? Zero potential node or datum node. The first important assumption is what? V1, V2, the principal node voltages are assumed to be at higher potentials with respect to reference node. Okay, this is first important assumption. Second important assumption is that when you are applying Kirchhoff's current law at node 1, this node voltage is assumed to be predominating over the other node voltages. Just an assumption. Okay, we do not know after solving V1, V2, we may get V1 10 volts and V2 minus 20 volts. We don't know that. But to proceed, to start with the problem, we make certain assumptions. These assumptions will help you a lot in writing down the equations. Okay. Now, what is that assumption? First assumption, V1, V2 are greater than this reference node voltage. Not only V1, V2, but also every node voltage is assumed to be at higher potential with respect to the reference node. Next, when you apply KCL at first node voltage is predominating over second node voltage and also other node voltage. Similarly, second node when you apply, second node voltage is assumed to be predominating over other node voltages. That's it. Okay? It's a very important assumption. Now, we would like to find current through each and every element. Yes or no? To find the current in any path, I told you very frequently I'm using the statement that to find current through any path, first you identify whether that path is having a resistor or not. For example, this one we'll see. Okay? Yes, there is a resistor, right? Find the potential difference across it. Where is this particular terminal operating? At V1 with respect to, always mention with respect to reference node. Where is it operating? E1, because this is 0. If this is 0, this is going to be what? E1. E1 with respect to reference node. Always express the voltage at a particular node with respect to what? Reference node. Otherwise, there is no meaning. There is no point at all. Okay? It doesn't make any sense otherwise. Now, what is the potential difference? Either E1 minus V1 or V1 minus E1. Anything is okay for us. That's not a problem. But what is your assumption? V1 is higher. Therefore, plus minus V1 minus E1. This is the exact meaning of branch voltage. What is this actually? Branch voltage is expressed in terms of node voltage. You understand? Branch voltages are in terms of node voltage. Clear? Now, once you know the branch voltage divided by this resistance will give you branch current. Also find branch current. Okay? Now, what is the direction of current? If you know polarities, you know the direction of current. What is it? V1 minus E1 by R. Clear? Similarly, here V1 branch voltage, node voltage same, because this element belongs to first node and zero node. Therefore, the reference node, therefore the voltage is, branch voltage same as node voltage. Therefore, V1 by R4. Here, V1 is higher. Therefore, V1 minus V2 I can assume, right? Then what is the current? V1 minus V2 by R3. Here, V2. V2 by R4. Here, V2 minus E2, because this is operating at what? E2. If this is 0, negative side if you take 0, then positive side you get what? E2 the same voltage you will get. V2 minus E2. What is the current direction? Based on the polarity same, right? Therefore, V2 minus E2 by R2. This is nothing but execution of second step, expressing the branch voltage in terms of the node voltage and also finding the branch currents. Yes or no? Okay. Then now let us apply the third step. Apply KCL at each principal node. Okay. Apply KCL at each principal node. At each principal node. Now let's apply. KCL at node 1. KCL at node 1. Assumption V1 greater than V2. Not only V1 greater than V2, but V1 is greater than any other node voltage. Understand? Okay. Now look at this. Current is leaving. Leaving current positive, entering current negative, let us assume. Now leaving current plus V1 minus E1 by R1. Leaving plus V1 by R4. Oh, I'm sorry, this is R5, okay? Please write it down. Here it is R5. Okay, now this is V1 minus V2 by R3 is equal to 0. This is first equation. Or I told you a method called inspection. Leave one line for it. Okay, I will explain you. Inspection is very interesting to apply KCL at node 2 now. What is the assumption? V2 greater than V1. V2 greater than V1. Now, if you apply KCL here, this current is leaving, right? This current is leaving, but this current is entering with an assumption V1 greater than V2. If you assume VT greater than V1, then current will leave. Yes or no? Here, V1 greater than V2, node 1, node 2, plus minus V1 minus V2. Therefore, current is flowing in this way. If you assume plus minus V2 minus V1, then current will flow like this. This is node 1, this is node 2. So as far as node 2 is concerned, current is leaving. But you must take V2 minus V1. Therefore, plus V2 minus V1 by R3. Then V2 by R5. Plus V2 minus E2 by R2. Or, I told you already, the inspection. Inspection is just derived based on our past experience, nothing else. Okay? We did so many problems, then we got some ideas. Based on that, we framed certain rules to write the equations without just bothering about anything here. Just directly look at the network and write the equation. That's it. Now tell me here, what are the equations? Please select the predefined sign plus here. Whereas in mesh analysis, I have chosen minus. It's all for my convenience, nothing else. Okay? And I'm selecting plus sign here. V1 of. What is the node voltage? V1 of. Sum of conductances at node 1 Nana. Whereas there, sum of resistances. Here, sum of conductances. What is conductance? Reciprocal of resistance. 1 by R1 plus 1 by R4 plus 1 by R3. Now, V2. Common element between first node and second node. And it's reciprocal. I want conductance, not resistance, okay? 1 by R3. And most importantly, predefined sign plus, then here it will definitely become minus sign. Because potential difference. Difference means what? Opposing each other. Okay? When opposing each other, predefined sign is plus, then the other sign will become minus. That's it. If it is minus, it will become plus. If it is plus, it will become minus. But whereas in mesh analysis, you must be always careful in checking whether the loop currents are flowing in the same direction or not. If they are flowing in the same direction, then off diagonal element sign is same as the diagonal element. Opposite direction, off diagonal element sign is opposite to the diagonal element. But in node analysis, it is very simple. If diagonal element sign is plus, off diagonal element is going to be, okay, minus, and vice versa. Okay? Therefore, here is equal to. Now, it's very, very important point. Okay? I hope you understand why plus minus I have selected here. This is predefined sign, then automatically you take minus sign. That's it. Now, at this node, you just identify, are there any branches? Are there any branches consisting of energy sources? No energy source. No energy source. But this path is having energy source. Branch means what? This entire path. Yes or no? This branch is having energy source. What is that? E1. So you must be careful here. Now is equal to, when you write here, look at what is our assumption we made. V1 is higher. That means current always flows from higher potential to lower potential. That means current is leaving and touching positive sign first. Therefore, plus E1 by its internal resistance. What is its internal resistance? Any resistance that is in series with an ideal source can be treated as an internal resistance. Therefore, this is R1. Equation 1. That's it. Simple. Now, second node. I think now you can easily write. What is that predefined sign? Plus V2. Sum of conductances. 1 by R2, 1 by R5, 1 by R3, 1 by R2, 1 by R3, 1 by R5. Yes or no? Now, minus sign, I told you already, you take minus sign just like that. Now, what is the common element and its conductance value? 1 by R3. is equal to, are there any energy sources at node 1? Any branch consisting of energy source? Yes, this branch is consisting of. So look at this. This is assumed to be at higher potential, leaving touching positive sign first, plus E2 by its internal resistance. I told you already. Second equation. That's it. Okay. Now onwards, we must be in a position to write directly the matrix form instead of writing these equations common. No. Let us write matrix form just by looking at the circuit itself. Understand all of you? Okay. So let us not look at here. Look at that network and tell me now. Okay. 2 by 2 matrix, right? So what is the predefined sign? Plus 1 by R1, 1 by R3, 1 by R4. Here plus 1 by R2, 1 by R3, 1 by R5. Yes or no? What is the common element here? Common element 1 by R3. Reciprocal. And this is plus, therefore it must be taken minus. I already told you. Okay. And this is, there is no need to look at this or waste your time. Don't think about it. Simply copy paste off diagonal symmetry minus 1 by R3. For this element, don't waste your time. Off diagonal symmetry will be always satisfied in this node and mesh analysis equations. V1, V2 is equal to, look at node, at this node there is a path with energy source. Current is leaving higher potential, touching positive sign first, plus E1 by R1. Current is leaving and touching positive sign first, second node, right? Plus E2 by R2. Therefore, simply apply Cramer's rule, delta 1 by delta, V2 delta 2 by delta. That's it. Apply Cramer's rule and solve the equations. I hope you understand. Please note down this. Please note down this. Okay. This is a case 1. I'm telling you, you are master in entire network theory part. And particularly if you are master in mesh analysis, node analysis, you are master in entire network analysis, I'm telling you. Okay. This part, I'm just erasing only the first line here. I think you have already noted down. Case 2. Case 2. Very interesting case, okay. This is also very important. You take any problem from any source, okay, from any place. I'm sure that that problem will definitely fall under any of these cases that I'm explaining here. Okay, that's why be careful in analyzing the networks with respect to all these cases. You must always generalize, okay. You cannot confine yourself only to a particular category of problems, because in the exam we do not know which category is going to give. There are infinite models are available, but the concepts are very, same. Problems may vary, the networks may vary, but the concepts won't vary, okay. So that is why let us be thorough with the concepts. Now here, look at this. How many nodes are there? Minimum number of nodes required to analyze this network. Tell me, how many are there? How many nodes you require? Look at this, how many nodes? Degree 2, not required. What is the minimum degree you require? 3. Degree 1, 2, 3, 4, therefore okay. Degree 2, not required. Degree 3, 1, 2, 3, yes, there is a node. We need to have a node variable here. This will become a principal node. So what is the principal node in our node analysis? A node with minimum degree 3. What is the principal node? A node with minimum degree 3. Yes or no? Of course, reference node can also be selected, no doubt in that. So the minimum number of nodes is nothing but the nodes with minimum degree 3, out of which one node is selected as a reference node. All remaining nodes are becoming what? Principal nodes. So this is also a node, okay, with minimum 1, 2, 3, 4, 5 degree here. So therefore this is also node. The degree is 2. I don't need to create a variable. The degree is 2. I don't need to create a variable here. Finally, you have 3 nodes, minimum number of nodes required. Select one node as a reference node, any node, but bottom node is usually selected. That's a common practice for anybody. V1 and V2. That's it. K-select node 1. K-select node 1. Okay? Tell me now. This point is operating at what? V1, this point is operating at what? E1, because this is 0. So what is the voltage here? The voltage at this node is what? E1. Yes or no? Now, in whichever the path you are trying to find the current, first identify the resistor, find the potential difference across it. That is V1 minus E1 divided by resistance. That will give you current. That's it. So what is the current flowing here? V1 minus E1 by R1. V1 minus E1 by R1. What is the current here? Please write down here. This is I4. Okay. What is this? Entering current minus I4. Now I am following leaving current positive, entering current negative. Now here, this path is having a resistor. Find the potential difference across it. Where is it operating? V1 with respect to reference. Where is it operating? E4. Look at this. This is 0, right? Therefore, this becomes what? E4. Then what is the potential difference? V1 minus E4 divided by R4. Therefore, V1 minus E4 by R4. Remember, you always follow the same logic. Whichever the path you want to find the current, first identify the resistor, find the potential difference and apply Ohm's law, you get the current. This must be fixed in your mind, that's it. Then you never do any mistake, I'm telling you. And I told you already that I'm explaining all these things in detail, keeping in mind all different varieties of students. Understand all of you, okay? Well, now, here, what about this path? This path, again, is there any resistor? Yes, there is a resistor. What is the potential difference across it? V1. Here it is V1 with respect to 0. Here, what is the voltage? Is it E3? No. It is not E3 because it is not 0. If it is 0, it is E3, but it is V2. Yes or no, all of you? Okay, this is V1. This point is operating at V1. This point is operating at what? This particular node is operating at what? Jump from this point to this point. V2 minus to plus, lower to higher. Take the voltage V2 plus E3. The voltage at this node is V2 plus E3. I hope you understand the point. Okay, I hope you understand the point. If I ask you what is the voltage at this node, you cannot say E3 because this is not zero. Understand? This is what? V2. The jump from this point to this point, V2 plus E3. This is the node voltage V2 plus E3 with respect to reference node. Anything that you find on the diagram at a node, the voltage, it is always with respect to reference node only. What is the potential difference? Higher, V1 higher assumption, V1 minus, V1 minus, V1 minus, okay, V1 minus, V2 minus E3. Okay, V1 minus V2 minus E3. That's it. V1 minus V2 minus E3. Potential difference divided by R3. So I think you understand why we are taking the expression V1 minus V2 minus E3. People remember it actually. Okay, no problem. You can remember, but you must also know how you have. Okay, how you have got this expression. The numerator is the potential difference across the denominator. The numerator is the potential difference across the denominator. Ohm's law only, this total one is potential difference by resistance. The numerator is the potential difference across the denominator. Equation 1. Understand? So, or inspection. One line you can remove. I mean, you can leave. Okay? KCL at node 2. Yes or no? KCL at node 2. Tell me. KCL at node 2. Tell me here. What is this now? The voltage, I mean, here you can see 0. This is what going to be what? That voltage is going to be what? E2 or minus E2? Because this is plus, this is minus. You're taking 0 towards the plus. Then this one will become what? Minus E2. Then what is the potential difference? What is the potential difference? Okay, plus V2 plus E2 by R2. Yes or no? V2 minus of minus E2. V2 plus E2 divided by R2 will give you current. And then what about this? Now you assume V2 greater. Then V2 plus E3 minus 1. Yes or no? V2 plus E3. V2 plus E3 minus 1. Minus V1. Nothing but V2 minus V1 plus E3 by R3. V2 minus V1 plus E3 by R3. Like that people remember. But what is the actual scenario here? This is V1, this is V2 plus E3. Now when you write KCL at node 2, you are assuming V2 greater than V1. Yes or no? Here you are assuming V1 greater than V2. Yes or no? Okay, that is why you select now V2 plus E3 greater than V1, V2 plus E3 minus V1. That's it. Now what about this? Is it V2 by R5 or simply I5 or anything else? See, irrespective of this resistor value, the current flowing through this path all the time is what? I5 only. Yes or no, all of you? Therefore, you should take just simply that current flowing through the path you already know, because an independent source, you already know the current flowing through this path. I5 is equal to 0. Some people say V2 by R5, why not it is correct? It is not correct because V2 is the voltage across the series combination of R5 and I5. The total voltage here it is what? V2. V2 voltage at this node is nothing but voltage between these two nodes only. How these two elements are connected? In series. Then voltage gets divided in series combination. Yes or no? Then how can you say the voltage across this one is V2? This is V2 dash. This is V2 double dash. I don't know what is that V2 dash and V2 double dash. Yes or no? That is why V2 by R5 is completely wrong expression. What is the correct expression? I5. And one more important point to be recollected here, that we already discussed this point. Any element in series with an ideal current source can be neglected or not. Yes, we do. Yes or no? Okay. Therefore, this can be neglected. But this element is neglected as far as V1, V2 voltages are concerned. But if somebody is asking what is the power of this current source, what is the voltage across this current source, can you neglect this? No. Understand all of you? For finding V1, V2, you can neglect it. But for finding power of this current source or voltage across this current source, you are not supposed to neglect. Please do remember all these concepts. Okay? Second. Now, let me apply inspection here. Plus V1 of 1 by R1, 1 by R3, 1 by R4. Yes or no? Minus V2 minus 1 by R3, sorry, 1 by R3, okay, is equal to, look at this, touching positive first, plus E1 by R1. The current is entering. Actually, entering current is what? Negative. But if you send it outside, you get positive. You have to remember it. Inspection means you have to remember. All these things we are, based on our experience, we framed our rules and then we are trying to write the equation directly, right? Therefore, this should also be remembered here. I4 is entering. I4 is entering here. That current is negative that side, but this side is positive. Now here, touching positive sign first, plus E4 by R4. Touching positive sign first, plus E3 by R3. This is the first equation. Understand? Okay. Now, this one, inspection. V2 plus V2, right? Plus V2 of 1 by R3, 1 by R2. Do you get 1 by R5? No, I told you already. You are neglecting this R5 because it is in series with what? An ideal current source. That's it. Minus V1 of 1 by R3 is equal to, yes or no? Okay? You're touching negative sign first. This is higher. Current is leaving, touching negative sign. Minus E2 by R2. This is the leaving current. Usually positive this side, but outside when you send minus. You must remember it. Touching negative sign first. Minus E3 by R3. This is the second equation. Now you must write directly the matrix form just by looking at that figure itself. Yes or no? Okay? There is no need to write all these things and waste our valuable time unnecessarily. And this inspection I'm telling you will help you a lot in finding the transfer function. Okay? So now let me write it clearly. 1, 1. What is that 1, 1 element? 1 by R1. Please look at the diagram and tell me 1 by R1, 1 by R3, 1 by R4. 1 by R2, 1 by R3. But do you get 1 by R5? No, never. Yes or no? Okay? Now, what about the common element minus 1 by R3? This is minus 1 by R3. Off diagonal symmetry, yes or no? Off diagonal symmetry. Always satisfied. Now, into V1, V2 is equal to, I'm just writing here that is equal to part, okay? That is equal to part I'm writing here. What is this? Look at the diagram, plus E1 by R1. Yes or no? Okay? Then plus I4, entering current, negative that side, but this side positive, plus E4 by R4, plus E3 by R3. Next, here, minus E2 by R2, minus E3 by R3, leaving current I5 plus that side, but this side you are sending minus I5. That's it. Please note down, all of you, V1 is equal to delta 1 by delta and V2 is equal to delta 2 by delta. Okay. So quickly note down all these things. So we'll stop the session here, and the next session we will deal with other different cases, case 3, case 4, like that. Okay. So just note down this. Meanwhile, you have still time to note down. Okay.